And we were able to demonstrate this trap by applying 370 volts to it. I've got a picture of the voltages that we applied. So on these two RF rails, we applied 370 volts at 32 megahertz. And then various DC voltages were applied to the outside electrodes. And one of the principal issues in this was that when you look at an ion trap and you decide how you apply your laser to it, you want to make sure that the cooling laser is not perpendicular to any of the principal axes of the trap. The principal axes of the trap can be thought of as the directions in which the ion's motion is uncoupled from the other direction. So if you sort of looked at a contour plot of a transverse section of the trap and you saw like an oval for what the contour lines were, you would say that the principal axes were along the semi-major axis and the semi-minor axis. In the surface trap, if you just apply RF to it and then you apply your DC electrodes symmetrically, the principal axes will be vertical and horizontal. And so if you have to bring a laser beam across the surface of the trap, that laser beam is going to be perpendicular to that vertical axis, and so it will not cool the ion's motion in that direction. So one of the things we had to figure out was how do we tilt these principal axes without introducing an offset electric field for the ion at the RF node. And so through some simulations, we determined that we could apply these strange voltages to the outside that would rotate the principal axes, and yet there would still be an electric field null at the RF null. And so that's what was the sort of final step in getting this trap to work. Now, unfortunately, there were some voltage breakdown problems with this trap, and shortly after we got it to work, the RF rails shorted to the DC rails, and so we're no longer able to apply voltage. So this project is ongoing in that they're still building these service traps, and hopefully we'll get some more in order to test them and work out some of the kinks that we discovered. Another one of the traps that we've tested is one fabricated at Sandia National Labs by Matt Blaine, and that consists of a backside edge here with two long, thin RF wires strung over the middle of it. And then these DC electrodes come in from the side, and those are the control electrodes. So this is a surface trap. All the electrodes are in one plane. What's interesting about this is one of the things that's interesting is these RF electrodes are actually comprised of sort of a chain link design, where you have a circular, and you can start to see it right here at the end of this picture. So this is a picture of where the RF electrode is attached to its base right here. And it consists of these circles with little sides on it, so that when the backside, the layer below this region is actually released, these electrodes, these RF electrodes, have some tension on them. They stretch out and they're taut over this length right here. And so this trap we weren't able to get to work, but we still have another one, and we're still in the process of trying it. So the downside to this trap is that its depth is reasonable, but I guess we aren't quite sure what the problem is at this point. So it's still being investigated. Okay, so now I'm at the end of my talk, and I just want to summarize what I've told you. In the first section, or one of the first sections, I talked about demonstrating corner shuttling in the T-trap. And this was important from the overall perspective of building a scalable ion trap technology, in that in order to move an ion from one part of your trap to another, you need to have these junction regions. And I talked about some of the problems associated with this, like the RF barriers and separating two ions that are in the same trap. And so that points to a few things that we could do in the future, or that other people can work on. And the main one I would want to highlight here is that we need smaller electrodes in order to improve our separation fidelity. Another topic was the motional heating of the ion and its scaling with distance and temperature, which we investigated in the needle trap. So future work on that is to test other materials. Like I said, we have a 2-needle trap that we're operating right now and that we've trapped in, that's made out of molybdenum and that has finer temperature control. Then finally, in this broader category of demonstrating microfabricated traps, this is an area that will get And a lot of the problems associated with it will be specific to the individual traps, because right now there are a host of different geometries and materials, and all of them have different problems associated with breakdown, just voltage application. So, and finally, I'd like to thank all of the people in my group, particularly on the microfabricated traps. Winnie Hensinger, John Sturck, Easter Mala, Steve Omshank have all contributed significantly to this project. And also Keith Schraub, who was one of our collaborators at the Laboratory for Physical Sciences, where I actually built these traps. He was an important component of this, as was Jim Rabchuk, and in doing some simulations. And also on the motional heating experiments, Louis Deloria was really important. So, thank you for your attention.